Hi Math 1030, this is lesson 10B, more geometry topics, and we have actually several varied topics in this lesson. So we'll do kind of a couple of examples of each, but really just a wide variety of topics here. So there's a lot of examples. So starting with some angle measure stuff, for many geometrical problems, especially those involving long distances, we need to measure angles precisely. So like in physics, when they're measuring the distance between planets or working with different planets or different galaxies or different stars, in those cases, instead of reporting angle measurements as decimal amounts like 42.38 degrees, it's more common to report angle measurements in degrees, minutes, and seconds. So in this system, instead of a decimal, you'll see it look something like this, where it's 42 degrees, 22 minutes, and 48 seconds. Now, minutes and seconds here are kind of a lot like time, minutes and seconds. So we have 42 degrees. The 22 minutes is a smaller portion of measurement. So in each degree, there are 60 minutes, just like there are 60 minutes in an hour. Each degree has 60 minutes. And then each minute has 60 seconds, just like time. So these are breaking up degrees into smaller units of measure. So our first example here is that we're going to convert each of these degree measures, which are in a decimal form, into degrees, minutes, and seconds of arc. So we're just converting it. So we need to have sort of three parts to our answer. We need to know how many degrees, how many minutes, and how many seconds. So we're going to work from right to left as we deal with this angle. Starting on the right side, 140 degrees is our degree measure. The degrees just are the portion to the left of the decimal. So we don't have to do a calculation for that. It just is 140 degrees. So now we have to work with the decimal part. Okay, well, we have a decimal of 0.32 degrees. So to get the minutes, you take that decimal and multiply it by 60, because there are 60 minutes in each degree. So we take that 0.32 and we multiply it by 60, and in that case we would get 19.2. So the minutes that we will record up at the top are the whole number part. That's what we will record up here. And we will use the decimal portion to convert into seconds. So we'll take those, we'll take that decimal and we multiply it by 60 again, because there are 60 seconds in each minute. So 0.2 multiplied by 60 gives us 12 seconds. And that is our final part of our answer. Oops, I'm missing my... Anyway. All right, so 140.32 degrees is the same as 140 degrees, 19 minutes, and 12 seconds. So on this second one, we'll kind of go through that same process. We're looking for the degrees, the minutes, and the seconds. So first of all, our degrees are right there, 34 degrees. that portion to the left of the decimal, the whole number amount of degrees is right there. To get the minutes, we're going to take the decimal part, 0.25, multiply by 60. In this case, we get 15. So that's our minutes. For seconds, we would take the decimal part, but in this case, there is no decimal part. It's like 15.0. So we have 0 seconds on this one. If we had a decimal part, we would take that decimal part and multiply it by 60 to get our seconds. Okay, so that is converting a decimal into degrees, minutes, and seconds. So we worked from right to left. So for example 2, we are working backwards. We have the degrees, minutes, and seconds. So we want to convert that into a decimal measure. So we're going to work backwards from what we were doing before. We're going to work from left to right. So we start with the seconds right here. We have 36 seconds. So we take those 36 seconds and we divide them by 60. To find out what portion of a minute. And we get 0.6. Now this is going to be the decimal part of the minutes. So what I mean by that is what we have now is we have 123 degrees and then 10.6 minutes. So we have the 10 minutes that we had before, and now we have a 0.6 with it. So then we kind of repeat that process. We take our minutes and divide by 60. So we have 10.6 minutes divided by 60, and we get 0.17667. I rounded after 5 decimals. Probably not necessary to keep that many, but I'm not sure how my math lab is going to round that. And so this number that we just got is the decimal part for degrees. So our final answer is that we have 123.17667 degrees. That decimal just goes with the 123 degrees, and I think it wants you to round to the nearest hundredth. Yeah, it says hundredth. So we would say 123.18 degrees. So we divide by 60, working from left to right. So if we do that on this next part B, we will start with the seconds, 58 seconds, and divide that by 60 to get a decimal, 0.967. That decimal part goes with the minutes. So now our number that we're dealing with is 8 degrees and 14.967 minutes. So we converted seconds to minutes. Now we're going to convert the minutes to degrees. So we're going to take that 14.96667 and divide it by 60 to get 0.249. So our final answer is going to be 8. Now this goes with that 8.249. So if we're rounding to the nearest hundredth, that would be 8.25 degrees. All right, so that was kind of our first topic. It was degrees, minutes, and seconds with angles. So you'll either be converting into decimal or converting into degree, minutes, seconds. So just make sure you have both of those sort of in your notes so you can refer to them. All right, so the next kind of relates to degree minutes and seconds a little bit is latitude and longitude. Now these examples are right here as in decimal, but it's actually more common to have degree minutes and seconds for latitude and longitude. Um, Latitude and longitude are used to help us locate positions on the Earth. So latitude is measuring north or south of the equator. So the equator is shown in red on this diagram. So if you're 30 degrees north, you're somewhere along this great circle on the Earth, not great circle. Or if you're south of the equator, south latitude would be below the equator. And then, so that's latitude, and then longitude is measured uh, as a position to the east or west of what's called the prime meridian. The prime meridian goes through a city in England. So we would be west, we would be located at some longitude west of the prime meridian, and like Asia, it is east of the prime meridian. So longitude and for longitude, it's measured between 0 and 180, east or west. So our first question is, which is farther from the South Pole? Guatemala City, which is 14.6 degrees north latitude, or Lusaka, Zambia, which is 15.4 degrees south latitude. Well, these are measured in relation to the equator. So because this is 14.6 degrees north, this means it is north of the equator, which means it's in this northern hemisphere somewhere. The second one is 15.4 degrees south, so that south means it's south of the equator. So somewhere on the south hemisphere, southern hemisphere. Our question is relating to the South Pole. Which one is farther? Well, the South Pole would be the bottom of the Earth when it's kind of shown like this. So which one is farther away would definitely have to be Guatemala City. Okay, second question relating to latitude and longitude. It tells us the latitude and longitude of Miami, which is shown right here. It's 26 degrees north, 80 degrees west is its location. The question is, what is the latitude and longitude of the location on Earth that is precisely on the opposite side of the globe? So like way on that other side that we can't really even see in this picture. So what we have to do, if you think about how latitude and longitude, sorry, if we focus on latitude first, latitude has to do with how far north and south of the equator. Well, if something is north of the equator, then the point on the opposite side of the Earth is going to be that same amount, but south of the equator, way over on the other side. So it's still going to be 26 degrees, but it's going to be south. So it's the same number of degrees, but change north to south. Or vice versa. If it was giving you a point that was on the south side, you would change it to north. Longitude is a little bit trickier, and if I had you in person with me and I could hold up a globe, I would be able to explain this really well. But if you're thinking about something on the other side of the Earth, for latitude purposes, it does definitely change from west to east, but it's not the same number of degrees. So what we have to do is we use, on the other side would be difference of one, it would be 180 degrees away. So we take 180 and we subtract that 80 degrees that we were given. So it's going to be 100 degrees east. So for longitude, use the supplement of the angle. Supplement, I can spell. So 180 degrees minus your given angle. So latitude keeps the same, longitude, use the supplement. And of course, it always changes from north to south and west to east, or vice versa. Okay, so next topic is called angular size and distance. So if you are thinking about looking at an object, the farther away that object is located from you, the smaller that it will appear. And that is called an angular size. So like this diagram right here, it has a coin. If it's, relatively close to your eye, it has a large angular size. If you pull that coin farther and farther away, the coin stays the same size, but that angular size is that it's getting smaller and smaller and smaller. So, what it has, we're going to do some calculations using this equation for physical size, and it actually has a lot to do with, you might recognize this part of it is kind of like a circumference equation. And so we're thinking about our eyeball as the center of a circle. We have some angle that's our angular size. The physical size is just a portion of the circumference. We take the angular size and divide it by 360. So this is basically just an arc length formula. So we're going to use this in two examples. In the first example, we are going to calculate the physical size. And then in our second example, our variable is going to be the angular size, and we're going to solve for that. So example 5, we know the angular size of the sun as seen from Earth is 0.53 degrees. And we know that the sun is approximately 1.5 million kilometers away from the Earth. We want to use that information to calculate the real diameter of the sun, which is its physical size. So that's going to be our variable. So our physical size of the sun is what we're calculating. Angular size goes in the numerator, so that's 0.53 degrees. We divide that by 360, and we multiply by 2 pi times by the distance, which is 150 million kilometers. So if we calculate that, 0.53 degrees divided by 360 multiplied by 2 pi multiplied by 150 million. Also, before I hit enter, it wants our answer in scientific notation, so I'm going to hit the mode button and just throw it into scientific notation really quick, and then quit. And now when I hit enter, it'll give me that answer in scientific notation. Now be careful to not don't miss that times 10 to the 6th. That's an important part of our answer. So our answer would be 1.39 multiplied by 10 to the 6th power. So that's the physical size of the sun. All right, now we're going to do one where we kind of work backwards, and our goal is to calculate the angular size. So if we fill in the parts of this that we know, we might, let's see, this is our physical size. So we're trying to find the angular size of a circular object that has a physical size of a 6-inch diameter. Our viewing distance is 7 yards. Now, one thing to notice straight away here is that the units don't match. Our physical size is given in inches and our distance is given in yards. So we are going to need to convert into the same units. I'm going to use inches as my units. So you could pick yards. It just depends. I usually go to the smaller one. So our physical size is going to be 6 inches, just as given, but our distance we need to convert. So 7 yards. Well, each yard is 3 feet, and each foot is 12 inches. So if we want to know how many inches are in a yard, it's going to be 7 times 3 times 12. Oh, let me take that out of scientific notation. So 252 inches. That's what we're going to use for our physical distance, and we do need those units to be the same in order to do this. Okay, so now we can set up our equation. Our physical size is 6 inches, so that goes on the left side of our equation. Angular size is what we're trying to figure out. I'm going to call that x just for simplicity. Over 360 is just part of the equation, times 2 pi is just part of the equation, and then multiplied by the distance, which we just calculated as 252 inches. So our goal is to solve for x. So what I would do if I was solving this is just calculate the number that is on the left side of the equation with the x. So we have 6 equals some number times by x. And that number is what I have highlighted. So in the calculator, I would kind of just think of it as a fraction, and the numbers that are on the top of that fraction are 2 pi and 252, and the number on the bottom of the fraction is 360. So I'm going to get a decimal just for funsies. 4.398. So again, I just thought about what was in the numerator and what was in the denominator on the right side of that equation. The x I just left, it's just there. So now that we have that coefficient with our x, all we need to do is divide. So we divide both sides of our equation by our decimal. And I wrote down 4 decimals. Whoops. If I were you, I wouldn't, retype that in. We already have more decimals than that on our screen. I would use them all. I would say 6 divided by, and then second answer, that bottom button with the negative, and that's going to use the prior answer. And so it's going to use all the decimals there. So we get 1.36, and it does say round to the nearest hundredth, and that is our angular size. If you had typed it in, it probably would have been okay with that many decimals. Yeah, so it's probably fine. All right, so that's how to calculate angular size. A little bit trickier to get the angular size than the physical size. All right, next mini topic here is pitch, grade, and slope. When you're talking about roads, sometimes what engineers or what signs will tell you is the pitch. Sometimes it'll also tell you the grade. So we're going to just talk about how those words relate. So when you talk about pitch, it's sort of like telling you the slope. It'll tell you the rise or how much vertical distance it goes up, and then it will tell you the horizontal distance. So when it says the pitch is 2 and 20, that just means it goes up 2 feet for every 20 feet in horizontal distance. So just like slope, slope would be rise over run. It could also be given to you as a grade. A grade is usually a percentage. So if it says that it's a 10% grade, that means 10 out of 100 or 1/10. So 1 in 10. So these words all kind of mean the same thing. They just are different forms of the same thing, I guess. So when you're talking about pitch, slope, and grade, a higher number means steeper and a lower number is more shallow. So for this one, we want to compare which one is steeper, a road with an 8% grade or a road with a pitch of 1 in 9. Well, 8% grade means 8 out of 100, or in decimal form, that's 0.08. I think it's easiest to compare the decimals. Pitch 1 in 9 is the fraction 1/9, which in decimal form is 0.111. If we want to know which of these is steeper, we're just looking for the bigger number, and the bigger number is this one. So the steeper is pitch of 1 in 9. I guess they usually use the word in. Okay, so that's another mini topic. Next mini topic has to do with Pythagorean theorem. So you are familiar with Pythagorean theorem. Leg squared plus other leg squared is equal to the hypotenuse squared. In my math lab, they're going to have you use the Pythagorean theorem to figure out the area in acres of a plot of land. So it gives us this right triangle. The length of this side of the triangle, it's really small, but it's 250 feet. And if you can't see this other side, the hypotenuse is 1,200 feet. So we want to find the area. To find the area of a triangle, it is 1/2 base times height. And so we need to know how long this leg of the triangle is. And that's where the Pythagorean theorems comes in. So we're going to first start by finding the leg with Pythagorean theorem. So I'm going to call it x. So x squared plus 250 squared is equal to 1,200 squared. So if we subtract, we can get that x by itself. 1,200 squared minus 250 squared. $1,377,500 is x squared. So then to finish up, we take the square root and we get 1,173.67. That should be okay. Now that we know that, I'm going to call it height, that height of the triangle, we can find the area. So the area is 1/2 of the base times the height. $146,708.75, and that was feet times feet, so that is square feet. Our last step on this problem is that we want to find the area in acres, and it gives us a conversion factor right here. So we're going to convert. So we're going to take our amount, 146,708.75 square feet, and we're going to multiply it by that conversion factor. 1 acre is the same as 43,560 square feet. So the units of square feet cancel out and we will have our acres. So we need to take our square feet and divide it by 43,560. And that gives us 3.37 acres if I round to the nearest hundredth. Okay, we are almost there. One last mini topic, couple examples. Similar triangles. Two triangles are similar if they have the same shape but not necessarily the same size, meaning that one is either a scaled up or a scaled down copy of the other. So when we work with similar triangles, we often use proportions to help us solve. And what we want to do is use corresponding sides in order to set up the proportions. So for example, we might use A in this triangle and divide it by A prime in the other triangle. And then we would use another set of corresponding sides, like maybe the C's. So we would have C over C prime. And you just want to be very consistent. If your sides from your larger triangle are on the top, then the sides from the smaller triangle would be on the bottom, or vice versa. And it doesn't exactly matter how you set it up as long as you have a lot of consistency with how you're setting it up. So here's an example. Determine the lengths of the unknown sides of the following pair of similar triangles. So I'm going to highlight the corresponding sides. So this corresponding side is going to be red. This one I'll color green. And the one at the bottom I'll color blue. So in my first proportion, I'm going to solve for A. So I'm going to use the red sides. So in the large triangle, it's 10, and in the small triangle, it's 5, so 10 over 5. And then I'm going to use the green sides in my other proportion. Starting with the large triangle, just like I did before, it's 10 over A. So I set up my proportion, and then I cross multiply that, which just means 10A is equal to 5 times 10 is 50, and then divide. So if we divide by 10, we get that A is 5, which probably makes sense to you. It's an isosceles triangle. And we'll set up a similar proportion to find side B. Again, using the red sides that we know, 10 over 5. In the larger triangle, we have the blue side is B, and in the smaller triangle, 7.5. So there's our setup. We cross multiply to get 5B is equal to 10 times 7.5 is 75. Throw it in your calculator if you're not sure, and then divide. So we divide by 5 to get 15. And for good measure, so these were kind of oriented the same way. One practice problem where they've twisted them around. So they have color-coded it in my math lab, so that should help. It looks like the sides that we know that correspond are the red sides, so we're going to use that to help us. First, finding A, which is the blue side here. So red over red equals blue over blue. So if we solve that, we get 28A is equal to 1764. And now we divide by 28 to get 63. And another setup for the green side. So 49 over 28 equals 70 over B. So if we cross multiply that, we get 49B is equal to 70 times 28 is 1960. And then we would just divide by 49 to get that B is 40. So that's it. Lots of random topics in this lesson. Let me know if questions come up or if some of these topics you found to be more tricky. I'm more than happy to do Google Meet with you and help you out. Let me know what comes up. This is the last section that will be in our Unit 4 exam. I think on the, I'm going to send out a correction, but on the review it said that 11B and C were included in it, but they are not. That was an error on the college's part, and they have modified it so that the test only goes through 10B, but I'll send out a calendar and everything for that. So let me know what questions come up, and as soon as you finish this lesson, you should start on the review for test 4. Thank you.